You know, every single day, we're faced with a world of incomplete information, whether it's trying to predict the stock market or just figuring out if you need an umbrella. So the big question is, how do we make the best possible guess about reality when we can't ever see the whole picture?
And that's exactly the question we're diving into today. We're going to unpack the amazing statistical tools that let us take just a small slice of data and make a really good guess about the whole thing.
All right, take a look at this chart. This shows the highest sea level that was recorded each year in a place called Port Pirie, Australia. Now, just from this data alone, how on earth could you predict the risk of a massive once-in-a-century flood? You know, the kind of event that only has a 1% chance of happening in any given year. Well, this is precisely the kind of high-stakes problem that statistical estimation was designed to solve.
So here's how we're going to break it all down. First, we'll talk about the main challenge. Then, we'll get into the real workhorse of statistics, the maximum likelihood method. After that, we'll check out a different approach for extreme events, see it all come together in a fascinating case study about water, and then we'll wrap it all up with the key tools for your own thinking.
Okay, so what we're really talking about here is something called statistical inference. And it's basically the science of using a small, observed sample of data to learn something meaningful and, well, to make an educated guess about the entire population that sample came from.
Right. Let's get into our first major tool. It's called the maximum likelihood method, and it was developed by an absolute legend in the field, Sir Ronald Fisher. Honestly, this is one of the most powerful and widely used ideas in all of statistics. At its heart, maximum likelihood estimation, or MLE for short, is actually super intuitive. All it's doing is asking a simple question. Given the data I actually have in my hands, what version of reality would make this data the most likely thing to have happened?
Let's make this really simple. Imagine you flip a coin 80 times, and it comes up heads 49 times. Kind of suspicious, right? You think it might be biased. So how do you estimate its true bias? Well, with MLE, you'd set up what's called a likelihood function. It calculates the probability of getting 49 heads for every possible bias the coin could have. The best guess is simply the one at the very peak of that function, the bias that makes your result most probable. And in this case, it's, you guessed it, 49 divided by 80. So simple, but so powerful. Now, MLE is amazing when you've got a decent amount of data to work with. But what about those really rare extreme events, like that 100-year flood we talked about? When your data is sparse, MLE can sometimes struggle. And that's where we need a completely different way of thinking. That brings us to the Bayesian approach.
And this is where things get really interesting, because this is a totally different philosophy. MLE basically assumes there's one single true answer out there, and its job is to find the best point estimate for it. Bayesian inference, on the other hand, says, well, the answer itself is uncertain, and it treats it as a whole range of possibilities, described by a probability distribution. This also lets us mix in our prior knowledge right into the model.
And it all comes down to this one beautiful little equation. You start with an initial belief, which we call the prior. Then you multiply that by the evidence you get from your new data, which is the likelihood. And what you get out is your new, updated belief, which we call the posterior. Put simply, you start with a hunch, you collect some data, and that data helps you update and improve your hunch.
So let's jump back to our sea level problem. For predicting something really rare like this, a Bayesian approach is often the way to go. And why is that? Well, because extreme data is, by its very nature, rare. You don't have a lot of it. Bayesian methods let you beef up that limited data with other info you might have through your prior beliefs.
And if we look at the results from the Port Pirie data, you can see what I mean. The first few columns are just different parameters for the statistical model. The last column is the one we care about, the estimated 100-year flood level. Now, you'll notice both methods give pretty similar answers, but here's the key difference. While this table only shows the single best guess from each method, the Bayesian approach also gives us a whole range of plausible values, which gives us a much richer understanding of just how uncertain we are.
Okay, so let's take all this theory and see it in action, in a place where these guesses have huge, high-stakes consequences. We're heading to Arequipa, Peru, where statistical estimation is being used to manage one of the most critical resources on the planet, fresh water.
So this is the area, it's a desert. You've got over 700 square kilometers of farms that need irrigation, competing with a city of over 1 million people and a huge mining industry, all for a very limited supply of water that comes from the Andes. Figuring out how much water the farms actually need is, well, it's absolutely crucial.
So to figure out what's growing where, researchers couldn't just rely on satellite images alone. They had to actually go out into the fields in these areas, see what the crops were, and record what they found. This ground truth data is basically the answer key that they used to train their statistical models.
And this is the incredible result. Using classification algorithms, which often use maximum likelihood under the hood, they were able to turn raw satellite data into these amazingly detailed monthly crop maps. You can literally watch the landscape change. See the areas in red? That's garlic. Watch how it shrinks after October. At the same time, corn, which is purple, starts popping up in November and really expands.
And check out how accurate these maps are. For major crops like alfalfa and garlic, the model was nailing it, with over 85% accuracy a lot of the time. The overall monthly average stayed really high too, which means these maps are a seriously reliable tool for decision makers.
So here's the final piece of the puzzle. By combining those super accurate crop maps with estimates about how old the crops were, the team was able to create these. These are actionable maps showing the actual agricultural water demand across the region. This is the kind of data that can help policymakers and farmers manage their precious water so much more effectively.
So what's the big takeaway here? Well, maximum likelihood and Bayesian inference aren't rivals. Think of them as complementary tools in a statistician's toolbox. You just have to know which tool to pull out for which job.
So if you remember one thing, make it this. MLE is your go-to when you have solid data and you need to find the single most probable answer. Bayesian methods are your tool for updating your beliefs about reality, especially when data is thin on the ground or when you really need to get a handle on your uncertainty.
From predicting floods to managing water in a desert, it's clear these estimation methods are incredibly powerful for making sense of the world. But you know, this is really just the beginning. The real question going forward is, as our world gets even more complex, how are we going to adapt these amazing tools to model and manage the massive challenges of the future?